Welcome to the course Structure Analysis. I am Dr.S.Pachaiappan, Assistant Professor, Department of Civil Engineering, Aditya University. So far, we have seen 14 lectures. So today is the 50th lecture. So last lecture we discussed about the distribution factor, and before that previous lectures we are discussed about the carryover factor and stiffness factor. So by using those distribution factor and stiffness factor and carryover factor, we are going to see today how to solve the continuous beam. Okay, and at the end of the lectures you are going to learn how to apply the moment distribution method to the continuous beam problems. Okay, so quickly I will take the example problem. So before discussing about the example problem, I first discuss what are the various steps are there to solve this problem. So let's discuss step 1. We are going to calculate the fixed end moments, and step 2 we are going to calculate the stiffness. Step 3 we are going to calculate the distribution factor. Step 4, the moment distribution table, moment distribution table, and step 5, we are going to draw the SFD and then BMD. So if you follow all these steps, we can able to solve the continuous beam by using the moment distribution method. So I will take one example problem, which is a continuous beam fixed at support A and fixed at support C. Support B is the intermediate support. Okay, support A, I have a UDL of 2 kilonewton per meter. Support B, I have the point load of 12 kilonewton, which is centrally placed at span BC. So this is 3 meters and this is 3 meters. Span AB is 6 meters and span BC is also 6 meters. So in this method, as we discussed, step 1 we need to calculate the fixed end moment. For calculating the fixed end moment, we need to go span by span. So I will take a span. So if you take a span AB alone and draw the free body diagram, which is having the UDL throughout the span of 2 kilonewton per meter and span 6 meters, this support A and B. Here we are going to have the fixed end moment MFAB, and here I am going to have the fixed end moment MFBA. Since UDL throughout the span, the MFAB, the formula is anti-clockwise couple, so I am using negative W L square by 12. So W is 2 kilonewton per meter and then L is 6 square by 12. So I will be getting minus 6 kilonewton meter. For MFBA, same formula but positive sign. Substituting the value, I will be getting minus 9 kilonewton meter. Sorry, this is also 6, same formula. After substituting, I will be getting plus 6 kilonewton meter. So we have just calculated the fixed end moment for the span AB. Now calculate the fixed end moment for span BC. Let's draw the diagram, span BC diagram. which is having the central point load of 12 kilonewton. This is 3 meters and this is 3 meters. Overall span is 6 meters. So what are the fixed end moments? Here we are going to have MBC, MFBC. Here we are going to have, so this is support B and this is support C. Let's write the formula for the point load at the center. So MFBC is equal to minus of WL by 8. So if you substitute this, minus of 12, L is 6 meters by 8. So I am getting minus 9. So then MF CB. So plus WL by 8. So I will be getting plus 9 kilonewton meter. We completed the step 1. So that is a fixing moment or fixed end moments. What about the step 2? Calculation of stiffness. Calculation of stiffness. So if you observe our beam, A is fixed, support A is fixed. So this is our beam, it is like this. A is fixed, C is fixed, B is simply supported. So in this case, we know the one end is fixed. One end is fixed and other end is simply supported. In that case, the stiffness is 4 EI by L. So for the member BA, the stiffness is 4 EI by L. For member BC, also the stiffness is 4 EI by L. The reason is, in both the span, we have one fixed support, another simply support. So we have written the corresponding stiffness values. Now step 3. In step 3, we need to calculate the distribution factor. So for distribution factor, just to draw the free body diagram of the beam. So this is A, B, C. Now I am going to consider the joint. So joint is intermediate support, which is B. And then the second parameter is a member. So from the B, we have the member BA, we have the member BC. From B, we have two members, one is BA, another one is BC. Then I am going to write the corresponding stiffness. For span BA, the stiffness is 4 EI by L. For span BC also, the stiffness is 4 EI by L. Let us substitute the value. This is 4 times of EI and the L is 6 meters. This is also 4 EI by L. Span BC also 6 meters. Now I need to calculate the total stiffness. Total stiffness is summation of stiffness at BA and summation of stiffness at BC. So the stiffness at BA is this value 4 EI by 6 and stiffness as BC is this value, this is also 4 EI by 6. So total we will be having 8 EI by 6. Now we are going to calculate the distribution factor. So what is the distribution factor? K1 by K. So this is the K1. This is the K2 and this is the value of K. Now K1 by K2 I am substituting. So K1 is 4EI by 6 divided by 8EI by 6. So these parameters will be get cancelled. Finally, we will be going to have 4 by 8, which is 1 by 2. In this case also 4EI by 6 divided by the total stiffness is 8EI by 6. So I will be getting 1 by 2. 6 get cancelled and then EI will be gets cancelled. I will be getting the value 1 by 2, which is 0.5. So we got the distribution factor. Okay. So step 4 is moment distribution table. Moment distribution table. Just draw the horizontal line, mark the supports A, and then B. So this is B and this is C. Make this as a table. Here I am going to put the distribution factor which we are calculated. For BA we got 1 by 2, for BC we got 1 by 2. Then I am going to write the fixed end moment which we are calculated earlier. Let us go back and see what are the fixed end moments we are calculated. For the span AB, it is minus 6 and plus 6. So for AB is minus 6, for BA it's plus 6. No, plus 6. Similarly for span BC is minus 9 and then plus 9. So just write that values here. This is minus 6 and this is plus 6, minus 9 and then plus 9. Now what we have to do, I will write that operation here separately. We just need to multiply this plus 6 with that value 1.5. So before that, just to take the sum of this value. So which is plus 6 and then minus 9. This value will be multiplied with the distribution factor 1.5. So we will be getting the value of minus of 1.5. We need to write it here plus 1.5 opposite to that sign. So in similar way here also we will be getting 1.5. Once again I explain. We need to add these two values. We need to add these two values, this value and this value. Both the value we need to add and then the summation should be multiplied with the distribution factor of BA which is 1.5. We will be getting minus 1.5. We need to write the positive sign. Similar way plus 6 minus 9. The summation should be multiplied with 1 by 2. So we will be getting minus 1.5. You need to write the plus 1.5. So this is the operation. Now from this 1.5, the 50% of the moment will be transferred to the support A and then 50% of the moment will be transferred to the support C. So 50% of 1.5 is 0.75. 50% of the 1.5 is 0.75 in both the supports. That's it. Hereafter I cannot able to distribute any moments and further steps are not possible. So draw the horizontal line and take the summation of this value. So we need to sum up these values which is 6 minus 6 and then 0.75. So I will be getting minus 5.25. Okay. So these values I am adding. Similarly these values I am going to add. So I will be getting plus 7.5 and this is minus 7.5 and this is 9.75. So these are our final moments. Very easily we got it. I will write MAB is equal to minus of 5.25, MBA equal to 7.5, MBC is equal to minus of 7.5, CV is equal to 9.75. Don't write, forget to write the unit. All moment units are kilonewton meter. Okay. So now we got the final moments. With this moment, we are going to draw the shear force and bending moment diagrams. So let's take the beam once again. So this is 6 meters. 6 meters. Now whatever the moment we got, that moment we need to write it here. This is 5.25 anti-clockwise, that's why negative symbol is coming. This is clockwise 7.5 and BC is minus 7.5, so anti-clockwise, and then this is clockwise which is 9.75. Now this is A, support B and support C. Support A we have the UDL whose intensity is 2 kilonewton per meter. Support BC, span AB, and span BC we have the load, central point load of 12 kilonewton. This is 3 meters and this is also 3 meters. So for calculating the reaction force, you know, we need to go span by span. So I am taking span AB. So let's take the span AB alone and then write down the load which is 2 kilonewton per meter. Okay. So this is 6 meters. We have a anti-clockwise couple of 5.25 and then another moment at B is 7.5. This is A and this is B. Now what I am going to do, I am going to taking moment at A, taking moment at A and then equate the clockwise couple and then anti-clockwise couple. So I am going to equate clockwise moment and then anti-clockwise moment. First of all, what are the clockwise moments are available here? The clockwise moment is, will be having, we are having the reaction RA. So this RA multiplied by 6 is rotating in a clockwise direction. So 6 times of RA and then this 7.5 is rotating in clockwise. So plus 7.5 equal to, what are the anti-clockwise? 5.25 is anti-clockwise and then load. This load is acting 2 kilonewton per meter multiplied by the perpendicular distance is acting anti-clockwise. So 2 into 6 into 6 by 2 which is 3. By substituting this value, I will be getting the value of RA is 5.625 kilonewton. 5.625 kilonewton. Now I need to use the equilibrium condition, summation of V is equal to 0. That means summation of all the vertical forces equal to 0. So now what are the vertical forces are there? RA is acting in upward direction plus RB1 also acting in upward direction. So whatever the reaction force is acting here, that is RB1. And then this UDL is acting in downward direction, which is 2 multiplied by 6 is acting in a downward direction equal to 0. Okay, so minus 12 is acting in a downward direction. So just now we calculated the value of RA which is 5.625. RB1 value we don't know, minus of 12 equal to 0. So RB1 is equal to plus 12 minus 5.625. So RB1 is equal to, we will be getting 6.375 kilonewton. Okay. So we got the value of RB1 and also the value of RA. This is for span A. The similar procedure we need to follow and do it for span B. So here I am going to have RB. Okay. So the moment we are going to have in both the support because of the fixed support. Here I have the central point load of 12 kilonewton, and this is 3 meters, and this is also 3 meters. Total span is 6 meters. Okay. So same principle we are going to do it here. I am going to take this is B and this is support C and our RB1. Okay. I am going to take moment at C, taking moment at the point C. So if you take a moment at C, then we are going to equate clockwise and then anti-clockwise couple. So RB2, this is RB2 because RB1 already we are calculated. RB2 multiplied by 6 is acting in an anti-clockwise direction. RB2 multiplied by 6 is anti-clockwise direction. Then what are the other moments are in anti-clockwise direction? Sorry, RB2 into 6 is acting in a clockwise direction. So, well, let's mark that moments. This is 7.5 and then this is 9.75 kilonewton meters. So, we will be having RB2 multiplied by 6. Then the clockwise couple is 9.75 equal to, another side anti-clockwise is 7.5 and then plus the load UD point load 12 into 3 is acting anti-clockwise direction. So if you substitute this value, simplify it, we will be getting RB2 is equal to 5.625 kilonewton. Now once again I need to use the equilibrium equation, which is summation of all the vertical forces equal to 0. So our RB2 is acting upward direction plus our RC is acting upward direction minus our point load is acting in a downward direction, which is 12 kilonewton equal to 0. RB2 recently we are calculated, which is 5.625. The value of RC I don't know, and this is minus 12 equal to 0. So RC is equal to plus 12 minus 5.625. I am getting the value of RC is equal to 6.375 kilonewton. So we calculated all the reaction forces. Now quickly we will draw the shear force diagram. For shear force diagram, I have to take the existing beam and marking all the loading condition, because for calculating shear force we need a load which is 2 kilonewton per meter, and here we have the central load of 12 kilonewton. This is 3 meters, 3 meters, 6 meters, 6 meters, span A, B, C, and we say this point is D. Now let us write our all the reaction forces. RA is 5.625, RB is 12 kilonewton, RC is 6.375 kilonewton. Now I am going to write the shear force at the point C. When you are going to right to left, I am going to consider the upward forces are negative, downward forces are positive. So minus of 6.375. Shear force at the point D is minus of 6.375 and plus 12, I will be getting 5.625 kilonewton. Then shear force at the point B is equal to 5.625 kilonewton. At B we are having 12 kilonewton upward force. So we'll be getting minus of 12, which is minus 6.375 kilonewton. Now I am going to do shear force at left of B. At left of B, so minus of 6.375, left of B I am having downward force which is plus 2 multiplied by 6, I will be getting 5.625 kilonewton. Now shear force at the point A is equal to 5.625 kilonewton, and then there will be the reaction force acting in upward direction minus of 5.625 kilonewton equal to 0. So shear force at A is 5.625, it is not 0. To validate and verify our results, we are substituting this value also, hence it becomes 0. By using these values, I am going to draw the shear force diagram here. So mark the supports, this is A and this is B and C and this is D. At point C we are having minus of 6.375 kilonewton. At D we have 5.625. At B also we have 5.625. At B we have another point which is minus of 6.375. At A we have 5.625. So all these values just now we calculated. Now how to join these lines? It's very important. So all the way this is coming down from between the C to D, there is no loading. So all the way it is going to travel horizontally and then it is going up. Again D to B we don't have any load, it will come like this, and then again it's coming down like this. And A to B we have the UDL. So this has to be connected like this. So this is positive, negative, positive and negative. This is your shear force diagram. In the same way we calculate the bending moment diagram also. So before calculating the bending moment diagram, I just need to consider my beam is simply supported, because I am going to calculate the bending moment by using the superposition method. So this is 2 kilonewton per meter and here I have the central load of 12 kilonewton. So if I draw the maximum positive bending moment for this is the parabola, and for this I am going to have the triangle, and this value is WL square by 8. By substituting the value of 2 and I will be getting 9 kilonewton meter, and this is nothing but WL by 4. So W is 12 and L is 6 meters, this is also 6 meters, 6 by L is also, give me a minute, so this is PL by 4, so PL by 4, by substituting this, or WL by 4, by substituting this I will be getting 18 kilonewton. So by superposition method, the bending moment diagram is look like this. This is support A and support B and support C. We have the bending moment value at support C is 9.75 we calculated. At support B we have 7.5. At support A we have 5.25. So this is the bending moment diagram of moment which is negative. On the top of this I am going to superimpose this diagram and then this diagram. So here I am going to draw this parabola which is 9 kilonewton meter, and this is 18 kilonewton triangle slightly up. So this is 18 kilonewton meter. Now this is our bending moment diagram. The portion which I am highlighting is our bending moment. So this is the bending moment diagram by superposition method. So in this lecture, we have learned how to apply the distribution factor and stiffness factor and solve the continuous beam by using the moment distribution method. And also we have drawn the shear force and bending moment diagram. We have drawn the shear force diagram and then bending moment diagram. So by applying this principle, it's easy to, you can able to apply the same principle to the different type of loading of a continuous beam and then draw the shear force and bending moment diagram. So thank you for watching this lecture. In the next lecture, we are going to discuss another continuous beam problem. There we are going to take a different type of loading condition. Thank you. Thank you for watching this lecture.